Welcome to the pre-recording of the review for the second midterm exam. So this is our second review. We have covered 5 chapters. There will be 5 questions. Covered 5 chapters in 3 lectures of each chapter, so 15 lectures. So there are 3 parts in this review. I will first talk about the most important points about the where, when, and how. Then there is a picture show. I've opted to take one representative picture out of each lecture. In some sense, this is a geometry course. If you can explain the picture or if you can tell the story of the picture in your own words, then you should be prepared for the questions. So there will be 5 questions also in the second part, and then I will briefly go over the 5 questions on the second midterm exam, the last time the course was run in spring of 2019. Okay, so first it is on Monday, 6 November. And second, you can opt for an in-class or a take-home version of the exam. So we have the chapters 6 to 10 on trapezoidal maps, Voronoi diagrams, arrangements of lines, Delaunay triangulations, and windowing queries. So we have covered many topics in this course so far. In this review, I focus kind of on the central ideas. So there's no way that this can be comprehensive, but I hope that it prepares you for the second midterm exam. So this is an open book, open notes, open internet, and you may also use a laptop. Grade scope should be used. Also, the answer should be within a Jupyter notebook. With additional drawings. So you can do the exam online at home. What mainly matters that you upload your answers in time. Your answers, if you have made a very nice drawing on paper, then you can take a picture of this and also upload this in Gradescope. If you start doing the midterm exam on Monday at 9 o'clock, then it might be that you get overwhelmed or you get sidetracked. Don't worry, your time is then not wasted. You can still do the take-home version of the exam. So the exam comes in 2 flavors. The second version of the exam actually contains the same questions, so the same type of questions, but they will involve computer experiments. So if you have been thinking about the questions, but kind of feel that you got stuck or don't have time to give a good answer by 9:50, then actually you can do the take-home version. And this is still very good for you to get somehow an idea of what you have learned in this course. So the 5 problems in the take-home would then be seen as 5 important homework exercises. Okay, so this is a senior undergraduate, beginning graduate course. So in the flexible way of running this course is that if computational geometry is extremely useful, if you want to use computational in your research or computational geometry, if that is your main area of research, then presenting a final computer project about the problems that have been of main concern to you is a good way to finish this course. In that sense, you can replace your final exam with a research computer project. And in class on Friday during the review, I will also explain more carefully how that would work. So the third project could actually already be a draft of your final project. So in some sense, you can't really. So for the midterms exam, you're extremely flexible, but for towards the final exam, you can't really decide on the day of the final exam whether you want to do a computer project or not. So in some sense, we are now in the last month of the course. This decision should kind of be made uh, very early on, preferably in the first week of November, whether you want to go for a final exam or for uh, a research computer project. Okay, let's start to review. So also on making the exam, making a picture is actually often the first step in solving a question. So what I did is I selected one representative picture for each of the 15 lectures. So we considered the point location problem. So at the left here, you see, you could think of the graph that you see. The edges are roads, the vertices are intersections where the roads are meeting, and and then you have the regions in between. You want to locate a point, and you want to do this point location very efficiently. So the tool what we defined there is a trapezoidal map. So for the example, you see that we have placed a bounding box around our map. And then for every vertex, we have drawn vertical extensions. We motivated the vertical extensions because if we would go all the way through, that would lead to a finer subdivision, but that would have led to a storage cost that was too prohibitively large. How do we construct these trapezoidal maps? Well, we are adding um, line segments incrementally. So we are starting out with our bounding box. We are adding line segments. And at the endpoints of the line segment, we are constructing vertical extensions. So here is one of the phases in the algorithm where our new segment, the S sub I, is intersecting several trapezoidal regions. So you see that the point location problem is already important here. If we have a new line segment, we locate the left point, find the trapezoidal, the trapezoidal the face where it belongs. Here actually it belongs, it's kind of special. It coincides with a vertex that was already there. So you can think of, again, the edges are roads, and here we have an intersection where three of the roads are meeting. And then we walk from the left to the right. So we have a data structure that captures this adjacency. So the construction is essentially also combined with a search structure. So we have the trapezoidal map, and associated to this trapezoidal map, we do have a search structure. Here is this. search structure, we are locating points by navigating this binary search tree. So we check whether we are at the left or at the right of the endpoints, and then whether we are above or below the line segments. So here you see an example where we first inserted S1, the first segment, and then S2. So that, and it's a tree structure, but every region in the trapezoidal map is stored only once. That's why you have two pointers coming to this E uh, subdivision, E region here, the E trapezium. So it's a directed cyclic graph. Okay, so the title of the lecture was expected cost and degenerated cases. So in order for everything to work efficiently, you must be able to locate a point efficiently as well. And typically this goes via a logarithmic cost. So the logarithmic in the total number of line segments. Now you will have a cost that is not logarithmic if your tree is very deep, or if your directed cyclic graph is quite deep. And this also motivated the randomization. So here is our first review question. So it's a rather beginner's question. Why would you need randomization? A very important question. So we've seen in this course several randomized constructions. Why do you need this? And also give a good example to illustrate the need for a randomization. So if you have solved the exercises, then actually you can answer this question already. So the exercises are low stake um, problems, so you won't fail the class if you don't do any of the exercises. But still, you actually will be very much unprepared for the midterm exams. So I do not want to give you any practical guidance on doing the midterm exam or not. But if you have been skipping exercises, then the midterm exam is actually a great opportunity to learn about the most important problems. So I can tell you the answer to this exercise. If you are intersecting with your next line segment, the last added trapezium that has been added, then your tree is getting deeper and deeper. So, or longer and longer. So the search path will get longer and longer. So you can think about a sequence of segments where the next segment is always going to intersect and therefore also replace the trapezia that were added in the last step. And that will lead to a quadratic algorithm. And why is randomization effective? Well, so that's also why this is a good exercise. You will have to think about this a little bit, especially if I would encourage you to use at least 3 line segments. But if you would think about the general recipe, and this is where the second part of the exam comes in, if you have to use a computer to define, for example, hundreds of line segments, then you can think about the recipe and an order of the segments. So what I'm saying is this is a good exercise. Such very bad cases are actually pathological. If you have n line segments, you have n factorial, and that can be a very huge number, n factorial ways on how to give them on the input. And those unlucky cases are among the whole universe of potential n factorial orders. They are small. Okay, second topic, Voronoi diagrams. Voronoi diagrams are a partition of the plane with respect to any given number of sides. So here we have 5 points, we call them sides, so P1, P2, P3, P4, P5. The picture focuses on the Voronoi cell for the first point, P1. So you can see that the edges of the Voronoi cell are segments lying on the bisectors. If you have to make a Voronoi diagram by hand, so 5 points, you draw all the bisectors. So here I drew only those bisectors that involve the first side. So there are 5 lines being drawn. At the vertices, we can draw circles. So here I only drew 2 circles. You can imagine 2 other circles on the 2 other vertices. So the circles are the largest non-empty, I'm sorry, the largest empty circles. Empty of any site. So it takes 3 points to uniquely define a circle. You can actually draw these circles or compute these circles by the edges of a Voronoi cell. So this is the characterization of the vertices of the Voronoi cell. So the Voronoi cell itself is shaded in green. There is also the edge characterization. So for any edge, you can also draw a largest non-empty circle. The diagonal is actually going to be the edge or part of an edge of a Voronoi cell. So here I drew 2 such largest empty circles. So again, these circles are important and they're kind of unique. They're characterizations for the Voronoi cells. How do we compute Voronoi diagrams? So the structure seems kind of involved, but the complexity of a Voronoi diagram is linear. That was an important result, which allows for an n log n algorithm. So the algorithm that we have studied is the beachline algorithm. So we sort the points from top to bottom. We imagine a line, so this is the sweep line, and the parabolas are defined by the sweep line as the directrix. So the 3 parabolas that you see, they all have the same directrix, and the difference between the parabolas are the focus points. These are the sites. So the definition of a parabola are all the points at the same distance from the focus, the site, and the directrix. So you have the beach line that is drawn in red here. We have the intersection of the parabolas. So as the sweep line goes through this, so this is a very nice imaginary geometrical construction. As the sweep line goes through this, we actually are sweeping out with the intersection points of the parabolas. We are actually tracing the edges of the Voronoi cells. Okay, so here are then the events. If you think about the algorithm, we have site events. So when the sweep line meets a new point, if it encounters a new point, we will have a new parabola. We will update the beach line. The beach line is stored in what we earlier called the status of a sweep line algorithm. But this comes from the line segment intersection problem. Uh, we have we have to check whenever we have an event whether we have new intersections. So we have to think about the circles as well. So here you see the bottom half of the slide indicates a circle event. So we have a site event and we have a circle event. At a circle event, we will create a new vertex. So you see here where the three parabolas meet. And again, the definition of a parabola is that we are at the same distance of the directrix, but also at the same distance of every site. And that's actually the characterization of a vertex of the Voronoi diagram that we are constructing. So we arrived at an n log n construction of Voronoi diagrams. The data structures that we were constructing were doubly connected edge list to represent the subdivision of the plane with all the Voronoi cells, and also a tree, the tree that represents the adjacencies of the parabolas. Actually, the parabolas are represented by the sites. Okay, so the events are kind of complementary. We have a site appearing and we have a site disappearing from view. So we are scanning the points. So we have an event queue. That's the initialized with the order of the points, sorted from top to bottom. But we will add to that event queue if we want to detect circle events. We have the structure that stores the Voronoi diagram, and then we have the structure which represents the beach line. The size of the beach line again can never be more than all the sites. There were many properties of Voronoi diagrams that we were using to show that Voronoi diagrams can be computed very quickly, just as you can sort numbers in n log n time. All right, here is then our review question. Here consider a set of points, 5 points. Draw the evolution of the beach line. What you will do with every review problem, you will draw these points, sort the points from top to bottom. So you have 5 points, you have 5 side events. Drawing the parabolas might be require a lot of paper. So if you make drawings, please make them large if you do them by hand. But also you can describe them. So you have to list the side events and you have to list the circle events. During the exam, you may actually also use software. So even if you are doing the in-class version of the exam, we've seen SciPy. SciPy allows, we always did it for random points. But here, if you do not want to draw on paper, you can use SciPy and do the Voronoi plot. Or if you have installed Seagull completely, you can use Qt to draw it as well. So there's absolutely nothing against it to actually um, do this. Uh, and what you could do also with SciPy is an incremental version. So you can, or you can do this 5 times, drawing the 5 different Voronoi diagrams and indicating at each time what is the beach line. Um, so you will discover there are new edges, new vertices that are being constructed. Make the connection with the beach line. Okay, we motivated arrangements for um, by the by a problem in computer graphs. And I'm sorry, I'm pausing here a little bit. So because there is a bug in this slide. Um, if you go to the corresponding lecture, I fixed it, but during my preparation, I was a little bit in a hurry. The vertical line should not be there. But the point of this slide is to indicate that at the left you see the original problem. We want to count the number of points below a line. The dual problem is that we want to count the number of lines below a point. So actually the Q star 1 should actually be a horizontal line. So counting lines is somehow lines are larger than points. This offers a different perspective. So, but the concept here is that we can go from the left, taking a line to 2 points becomes the intersection point of 2 lines. The 2 lines are the dual of the points. If you read from right to left, the 2 lines become points, and since the 2 lines at the right intersect a point, they are lying on a line through those 2 points. So there is this very nice duality between lines and points. Okay, so we studied subdivisions, um, subdivisions that are defined by lines. Um, so here we have a new blue line that is up that is going to change a subdivision that is defined by, if I count correctly, by 1, 2, 3, 4. So these are 5 lines. So the existing subdivision is defined by 4 lines, and there is a new blue line that comes in, and the vertices are intersected. So we have new vertex points, and we're going to cut edges. So the edges are represented twice by twins. So we have edges inside, we run clockwise, outside we run counterclockwise. So in some sense, the uh, doubly connected edge list is an important data structure throughout the course. It was important in the first part. Here it is resurfacing again. And actually, I talked about it also with the Voronoi diagrams. The area here in yellow is indicating is focusing on one face. So one of the review questions is to spell out in detail what happens when you split a face. So we are walking our subdivision, which is actually the line arrangement, this type of subdivision. We are walking we have ordered all the points, all the vertex points already. We have done a pre-processing. We can sort the points from left to right. So we have an incoming edge and an incoming edge, incoming vertex, and we also have an outgoing vertex. The zone theorem was an important theorem, so I'm actually labeling the slides corresponding to the titles of the lecture. And I'm trying to narrate the essence of each lecture. The zone theorem had a different picture. The incremental construction of a line arrangement worked because the number of faces in the subdivision that were cut by a new line is linear in the number of total line segments. So it's not quadratic. So that's important. Returning back to the counting of the um, points, so we can actually count that was with the discrepancy problem. So if we have a line arrangement, we actually count the number of lines that are above each vertex. And you can see that we can solve this question by walking on the lines from left to right. So if we start at the top left and going down, we start initializing at 0. If we, at every intersection, we remember that there was an intersection. So we were intersecting, we are going down, we are intersecting with an upward going line. So at the next intersection point, there must be one line then above. So this is why we mark a 1. Again, we are intersecting a line that goes upwards. Then at the next intersection, we increment that again. So the counting of the number of lines above a point, above vertex points, can be done in linear time. So in a time that is linear in the total number of lines. And that is important. That is a very important result. This is why line arrangements can be applied. The zone theorem is an important theorem on its own, and it has important consequences on the construction cost. Okay, so if you are constructing an arrangement of lines, then we are intersecting a face with a line. So this exercise or this question here is important for the data structure, the doubly connected edge list. You can draw, but the answer also here, you can take the example of if to solve this question, you can take an example on the previous slide and actually define the table of vertices, the table of edges, the table of faces, and explain what happens when you are splitting a face. We've seen the algorithm. So you have an incoming vertex and you have an outgoing vertex. So the incoming vertex lies on an edge. That edge need to be splitted. And also, so there is a new vertex. So one needs to update the vertex table. We have, and then at the right, we also split vertex. We split an edge there. Except when the vertex is already existing. So you have to take care that your incoming vertex may be already a vertex that is off the face. If that is the case, then actually you will not split an edge. So that's an important if statement there. So I'm not going to flip the slides back, but we had the yellow face in the line arrangement. Look at the picture there um, and see what is happening. So all the questions, by the way, they can be solved in about 5 or 10 minutes time. And that includes the reading of the problem. So spend some time reading the problem, and then you have to write about a paragraph or two on the answer. Delaunay triangulations, they are they are maximizing the minimum angle. So here you see one of the pictures that defines an edge flip. So it's perhaps not entirely directly clear, immediately clear if you look at this picture, but perhaps intuitively you might you might recognize that the picture at the right with the beta angles is actually kind of better as far as the angles goes than the picture at the left. There's a formula that goes here. The minimum of all the alpha angles is less than the minimum of all the beta angles. That's the definition why we do an edge flip. So we are replacing the edge between Pi and Pj by the edge PK/PL. So that leads to a better triangulation that has a largest, smallest angle. So if we construct a Delaunay triangulation, we solve an optimization problem. If we compute Delaunay triangulations, actually we can do it already via the dual of the Voronoi diagram. So one algorithm for computing a Delaunay triangulation is computing a Voronoi diagram, and then by connecting the sides in the Voronoi diagram, connecting them by an edge if they are in adjacent Voronoi cells. So we had the circle characterization of Voronoi diagrams. We can draw these circles as well, and they will be important in the decision on whether we need to flip or not. So one can compute all the angles and you can dust off your vector calculus, but actually the circle characterization will actually provide a geometric criterion on when to flip or when not to flip. So we have we can impose on a Delaunay triangulation the Voronoi diagram. Or if you have algorithms to compute Delaunay triangulations, you also have a Voronoi diagram. Okay, for in the chapter 9, we um, discussed an algorithm to compute Delaunay triangulations incrementally, adding points one at a time. So you see that after adding the point here, we broke up the initial triangle. So there is a directed cyclic graph that is used to navigate. So Delaunay triangulations can also be used to solve the point location problem. So if we are adding a new point, we are replacing a triangle by new triangles, but then we have to do edge flips. So here you see the edge flip that is being done, replacing the triangles delta 2, delta 5 by delta 6 and delta 7. The delta 2 is still there for the point location. Just like the delta 1, it's not drawn here, but it was this very big triangle before the middle point was there. So we have a directed acyclic graph that is being maintained while we are constructing the Delaunay triangulation. All right, the circles. So this exercise here relates the difference, the distance between any point and any other point in a triangle. So to solve this problem, you should think about the characterization of the circles. So it is important to actually say something. uh, if you So in solving this exercise, you take one triangle, you draw the circle, and then what can you say um, from the distance? And in particular, what can you say from any point to any other point outside the triangulation? Um, Being inside the triangle means that you are in a Delaunay triangulation which optimizes the angles. So that is an argument that you have to use here as well. Okay, I'm running a little bit faster because I only have 10 minutes left, and I still have to go through the last chapter. The last chapter was done in the previous week, so I hope that it's still fresh in mind. We want to select points within a window. You can think of zooming in into a map. You could think of building a flight simulator. You have really your window that passes by, and you want to show only what is relevant inside the window. Here is one first relaxation of the problem where we consider vertical segments, intervals, and it's already here organized so that the intervals that contain the medium actually are listed on top. So we will have a tree which one root and two nodes. At the left, all the points that do not contain the median, and at the right, all the points that are to the right of the median. So this is a very intuitive way to make a tree, and that allows the vertical point location, to select the segments in a very quick way. Um, we can use a data structure that stores points integrating both the x and the y coordinates. So we've seen KD trees earlier, but for windowing queries, especially if the query window goes all the way to the left, so you can think about really the left as being the direction which you are flying in your flight simulator, then the leftmost point is most important, and in a heap or priority search tree, it will be uh, very close to the root of the tree. So 3 is the next one, and then 1 is the next leftmost point. So the height in the tree indicates how you are to the left. The left and right, left child or right child, indicates if you are above or below the median line. So we also subdivide the points again recursively on their height. Segment trees are data structures which locate kind of go back to interval trees, but we have a segmentation of the input segments. So we chop them up using the endpoints. So we have a number of intervals lined up here. We sort all the endpoints. That is, so the elementary intervals are at the leaves of the segment tree. And then inside the nodes, we store the segments, so the intervals that are given to us on input. And we store them as high as possible, as close as possible to the root. So this gives a very efficient data structure. And we use this data structure to locate the slab in which a line segment is. And then we have an extra data structure at each node. At each node, we will store more segments, more than one segment, and they are ordered concerning the height. So there is a binary search tree that orders the segments that are stored at each node. That's why the search is square of the logarithm in the total number of line segments. Here is our review exercise. We have a number of segments, construct a number of intervals, construct the segment tree to store this. You will order the endpoints, construct the elementary intervals, order the points from left to right, all the points, so 89 has to be all the way to the right. And then you have here 8 intervals. You then, in the second stage, you place these intervals at the nodes, using the principle that at the node, the intervals that you store there contain all the intervals of the children. But you cannot place them any higher. So they are as high as possible. So any input interval will be stored at most twice. Okay, there was a midterm exam 4 years ago, or almost more than 4 years ago. I will briefly go through the questions. So when does the order of line segments, when does it not matter? So again, this is a first question. It should be a confidence booster section. So it's kind of the complement of the randomization. Why do we randomize? So if all these segments are actually so far apart, so they are not overlapping, if you think about the intervals, the projection of them, so they are neatly separated. So, and no matter how you order them, it doesn't really matter. So just draw an example of this. Circle and site events. So here we have two input sites that are on top of each other. Does it actually matter? If we hit the lowest point, does that matter? Does it matter to the construction of the Voronoi diagram if you have the same coordinates, the x coordinates? To answer this question, you have to draw the sweep line. You have to indicate what is the Q, and also you have to indicate what are the parabolas here. You could also be more extreme. What if all the points are lined up into each other? Is this so? We've seen that for collinear point sets, the Voronoi diagram is very simple. And this is also actually the case here, if everything would be aligned neatly. Arrangements of lines. Suppose that instead of you would have a triangulation Could that be possible? For which arrangements of lines is this possible? Um, that you have only triangles? Suppose that your line arrangements that you consider would be like that. How can you improve the algorithm, of course? Or would this be so absurd that this general is not really going to happen? So we when we discussed line arrangements, we also talked about general position. Actually, the example, we had a new line, the blue line, which was intersecting an existing vertex. So that's even a more degenerate example. But what if you would have something that would be a triangulation? For which type of arrangements does this happen? Okay, Delaunay triangulations and edge flips. So the review question was asking for the circle. Here actually you have two triangles, and one of the vertices is actually a parameter. So we have the origin, the standard simplex, and then we have the AA. So if it is 1, 1, then it lies on the edge. So you can't really, so you should actually make a drawing here. I'm just running out of time. I'm saying what it is. But if you make the drawing, it will become clear. For which parameter is the triangulation of the Delaunay triangulation? And I can give you the answer. It's 2, comma 2. So they're actually, and that's the boundary case. Where after a equals 2, you have to start flipping. Okay, windowing queries. What if all the points would be on the unit circle? So think about an octagon, a regular octagon. What you have in that case is that you have actually points at the same height. Does this make a difference? What if you always would need to work with um, point configurations that are on the unit circle? Would polar coordinates be beneficial or not? That's the question here. Okay, I'm at the end of the review and I'm 2 minutes over time, more than 2 minutes over time. I hope that this review was somehow helping and not really making you more overwhelmed than you might be. Hopefully not. But there are some key principles that are occurring all the time in this course. And I hope that these principles are getting through.